Hi, welcome back to lecture 20 of MA 221, and today we'll be discussing about ratio and root test. So, what's the statement for ratio test for absolute convergence of a series AN? Let rho denotes the limit of the ratio AN plus 1 over AN, modulus of that, and n tends to infinity. Then I have three cases. If rho is less than 1, then summation n equal to 1 to infinity converges absolutely. Okay. We have discussed what is the meaning of absolute convergence before. If rho is bigger than 1, then summation n equal to 1 to infinity an diverges. So if you forget what is absolute convergence, you can look back in lecture 19, discuss it there. And the third result is if rho is 1, then the test kind of fails. Okay. Test fails means we can't say anything about convergence. Okay, cool. Right now the proof is out of scope, so I'll skip that and focus on some examples. So the first example is asking, is 5n squared over 3 to the n, this series converge or not? So remember I have to, and we will apply ratio test, and we need to find the limit of this ratio, okay? So suppose my an is the term of the series, which is 5n squared over 3 to the n. Then, of course, an plus 1 will be just replace all the n with n plus 1, like this. And then the ratio an plus 1 over an, limit n tends to infinity. So this becomes, so as all of the terms an plus 1, all of these are positive only. So we can neglect the modulus here. We'll get the same quantity, 5n plus 1 whole square over 3 to the n plus 1 over 5n squared over 3 to the n. And what is that? That is basically limit n tends to infinity, 5n plus 1 square over 3n plus 1 times 3 to the n over 5n square. Okay, so this and that cancels and gives me 3. Now for the rest of the part, limit n tends to infinity, 5n plus 1 whole square over 3 times 5n square. Of course, this 5 and 5 also go away. So I'll have this. Now we have tackled this type of limit before. What we have to do, we have to basically take n square out. So can do like this, n times 1 plus 1 over n square over 3n square, limit n tends to infinity. And then what happens is limit n tends to infinity, n square 1 plus 1 over n whole square, 3n square, n square goes away. And this is basically 1 plus 0 square over 3, which is just 1 over 3. Okay. Okay, so, and now if I go back, if it says that if the limit of the ratio is less than 1, then the series converges absolutely. So, and we see that 1/3 is of obviously less than 1. So therefore summation n equal to 1 to infinity 5n square over 3 to the n converges absolutely. Okay, cool. For the next example, we have e to the n over n to the 100. So an will be e to the n over n to the 100, and an plus 1 will be e to the n plus 1 over n plus 1 to the 100. Same thing as before. And then limit n tends to infinity, modulus an plus 1 over an is just limit n tends to infinity, e to the n plus 1 over n plus 1 to the 100 times n to the 100 over e to the n. Okay. And then after cancelling this and that, I have e, and then I have e n to the 100 over n plus 1 to the 100. Again, the same sort of argument we'll use it here as well. So n to the 100 times 1 plus 1 over n to the 100. Okay. So this and that cancels. Okay. This line is exactly same as the previous problem. There I have taken n factored out. Here also I have taken n factored out, but there is to the 100 there. So that's why I have got this n to the 100 outside. Okay. Not hard to see. And then at the end, I'll have e over 1 plus 0. So just e. And e is something like 2.7 and so on, which is obviously bigger than 1. And remember, our result says that if the limit of the ratio is bigger than 1, then the series diverges. So summation n equal to 1 to infinity e to the n over n to the 100 diverges. Okay, sweet. For the third example, I have n factorial times 2 to the n over 2n factorial. So again, I'll take an as n factorial times 2 to the n over 2n factorial like this. And an plus 1 factorial, an plus 1 will be just replace all the n with n plus 1. So 2n. So here, be careful. If I replace n plus 1 in place of n, then I'll get 2n plus 2. Okay. So when you are calculating what is the expression for an plus 1, be careful. Okay. You have to replace n plus 1 in place of n. Okay. So you can see that this n is the analogy is there. Okay. And now, okay, I would like to write one more line. So n plus 1 factorial that I can write as n plus 1 times n factorial, right? No problem in that. And then okay, so then I have 2 times 2 to the n like this. And on the bottom, I have 2n plus 2, and then 2n plus 1, and then 2n factorial, right? So I'm just rewriting it a little bit smartly so that I can so that I can cancel terms a little bit nicer when I evaluate the ratio. So I have n factorial times 2 to the n over 2n factorial, and then I have like 2 times n plus 1 over 2n plus 2 times 2n plus 1. Okay, just shuffling out terms. And then if I try to compute the ratio, then this is limit n tends to infinity 2 times n plus 1. Okay, so you can see that if I try to like calculate the ratio, then this and that we cancel out with this and that. Okay, that's why I'm like collecting and reshuffling terms. Okay, so I'll not write the terms that will like anyway cancel. So basically I will be left with this terms. Okay, fine. So now this is nothing but limit n tends to infinity, and so this, so 2n plus 2 on the top, and on bottom I have 2n plus 2 times 2n plus 1. This and that cancels. So I'm left with limit n tends to infinity 1 over 2n plus 1. So if I put infinity there, then I'll have 1 over infinity, which is 0. Okay. And 0 is of course less than 1. So by the ratio test first incident, I'll say that summation n equal to 1 to infinity n factorial 2 to the n over 2n factorial converges. Okay, but there are some cases where the ratio test fails. Okay, for example, if I consider summation 1 over n square, we know this is convergent, but using something else. If I try to like blindly apply ratio test there, then what will happen? So I'll be taking an to be 1 over n square, and an plus 1 will be 1 over n plus 1 whole square. Yeah. So limit n tends to infinity, an plus 1 over an modulus will be limit n tends to infinity. It'll be like n square over n plus 1 square. And then again, the same sort of trick to calculate the limit here. Take n factored out, 1 plus 1 over n, then square inside. So this is limit n tends to infinity, n square over n square, 1 plus 1 over n whole square. N square cancels. Then I have limit n tends to infinity, 1 over 1 plus 1 over n whole square. So this is basically 1 over 1 plus 0 square, which is 1. Okay. So if I go back to ratio test, the third scenario, when I have the limited the ratio to be 1, then we cannot conclude anything. Okay. So therefore, in this case, I can see that the limit of ratio is 1. So can't conclude anything about summation 1 over n square using ratio test. And then we have to like use something else, some other test to justify that if the series is converging or not. Okay. The next test is called root test. So let me write the statement of that. So let R is limit n tends to infinity, square root of, nth root of modulus an. Then also, just like the ratio test, I have three scenarios, 2 and 3. If r is less than 1, the series converges absolutely. Okay. If r is bigger than 1, the series diverges. And if r is 1, the test is inconclusive. Okay. Let me show some example for ratio test. Okay, so this time I have n equal to 2 to infinity summation 1 plus 1 over n to the minus n square. Okay, so here if I take modulus of n to the 1 over n, then I'll get 1 plus 1 over n. So this is like summation n. Yeah. So this will be 1 plus 1 over n and then minus n square over n, right? Which is nothing but 1 plus 1 over n to the minus n. Okay. Then if I consider the limit n tends to infinity n to the 1 n, then this will be limit n tends to infinity 1 over 1 plus 1 over n to the n. Okay. Before going into that, let me write some important limits of some functions because those will be helpful in ratio test, root test. Some useful limits. Okay, so limit of n tends to infinity n to the 1 over n is 1. How? For that, if I consider e to the ln n over n, so yeah, I can write the function like this. Okay, let me just, this is nothing but e to the ln n to the 1 over n, right? Because e and ln are like inverse functions. So e to the ln will be like this two will cancel out and will get back n to the 1 over n. And then this is nothing but let me write it properly. So the ln n to the 1 over n. And then by the law of logarithm, I can take this 1 over n in front. So I'll have e to the ln n over n. Okay. And when n tends to infinity, this is basically e to the 0, which is 1. So that's how the limit n tends to infinity n to the 1 over n is 1. By using kind of similar logic, we can say e to the 1 over n is 1 and limit 1 plus k over n to the n is e to the k. Okay. These three things can be proved, but the main idea is this. This sort of logic will be useful in proving those. Okay, anyway, the proof are not important. Okay, so by using the third limit, this quantity is nothing but 1 over e, right? And again, this is like 1 over 2.7 something, which is less than 1, right? So by ratio test, um, again confusing, by root test, summation 1 plus 1 over n to the minus n square 2 to infinity converges. Okay. Next, I'll try to sum up all the tests that I have discussed so far and how. So, supposing in the exam you are given with a random series and the question is asking you to conclude about the convergence or divergence of the series, then how we should proceed. So, I'll try to sum up the general strategy that you should follow. So, number one is what you have to remember is n equal to 1 to infinity 1 over n to the p. This is called p series. And for p greater than 1, the series converges. And when p is less or equal to 1, the series diverges. Okay. Number two is, before that, summation r to the n equal to 1 to infinity. This is called geometric series. And it converges when r is less than 1. And for r is bigger or equal to 1, this diverges. Okay. Number two is the divergence test. If limit n tends to infinity, modulus of an is not 0, then the series diverges. Okay, this is the system. Number three is if the series uh, looks like a p series or geometric series, for example, rational expressions, or square root of polynomials. Look at dominant term. And use comparison test. Okay. So if you can find a pattern like P series or geometric series hidden in the basic term of the series, then try to see what is the um, what will be a suitable um, you know suitable P series to compare with that. And then you can use either direct comparison test or the limit comparison test depending upon the situation. Number four is if you see factorials or say power, try ratio test. If you see, an is like Pn to the n, again, sort of like a power. Then where Bn is simpler, try the root test. So again, if you see power, then most of the time root test is like more suitable to use rather than ratio test. Um, oh, okay. I missed one point before this. So, I forgot about alternative series. So if you see terms alternate in sign, try alternating series test. And then for the last step, if an, you can write it as a function fn, and the function is decreasing and integrable, try integral test. Okay, and one note there is, if modulus of the series converges, then the series also converge. Okay, yeah. So that is the like basic strategy that you should follow when you see a general example. And this is it in terms of ratio and root test. I hope you'll be able to solve the homework problems. And if you have any problem, see you in the office hours tomorrow. Okay, thank you.